Welcome to our video on automated machine learning, or AutoML for short. Today we'll provide a very brief introduction to modern ideas for automating various stages of your ML engineering pipeline. We'll begin by providing the main definitions for AutoML. That way we know what types of problems we're going to be trying to address in the remainder of the video. Next, we'll go over ideas related to hyperparameter search, typically the first stage that an ML engineer will want to automate, and for which there are relatively straightforward approaches that perform well. Next, we'll move on to the more complicated approaches for architecture search. This aims to automate the design of neural networks for a particular task or dataset. Lastly, we'll address the elephant in the room, hardware limitations. The largest barrier to entry for taking advantage of AutoML is that it typically requires massive amounts of computational resources, at least for now. So, when we say AutoML, what do we mean? Although the term AutoML doesn't have a clear-cut definition, it generally refers to any method that helps automate the tasks that traditionally require experienced machine learning engineers to carry out. The goal of AutoML is to make machine learning available for everybody, even those that don't have a background in machine learning. Since this is still a bit vague, consider the two examples that we'll be covering today, which are typically what people think of when they say AutoML. First is hyperparameter optimization. Once we've designed the architecture of our network, there is often a lengthy process that follows when we experiment with different values for the learning rate, number of layers, dimensionality of certain states, stuff like that. This process also requires a good deal of intuition regarding which values are worth tuning and which values are best left with defaults. This intuition comes from years of experience and study, which by itself is enough to deter some people without a machine learning background to try integrating it into their workflow. The next and considerably more ambitious example of AutoML is automating the design of the neural network itself. In other words, we might specify that we'd like a neural network that can classify a particular image dataset, and our AutoML tools will give us a neural network architecture tuned specifically for that task. As we will see today, most current methods do this by exploring a large number of different candidate networks, training each separately. And unsurprisingly, this requires vast amounts of computational resources to complete in any reasonable amount of time. Okay, so for our first example, we'll consider how to automatically find a good set of hyperparameters for our neural network. A simple and surprisingly effective approach is called random search. In random search, we specify a range of values to try for each of the hyperparameters we're interested in, such as the learning rate or vocabulary size. Then sample a random value for each hyperparameter and train our neural network using those combination of values. This is similar to the naive approach called grid search, but can often find better configurations with less resources than grid search, as nicely illustrated by the figure on the slide. So this figure is for the case where we have two hyperparameters, and we want to find the best values for these two hyperparameters, such that our loss, or whatever surface we're trying to minimize or optimize, and is often not straightforward to know beforehand which parameters are more important than others for minimizing this function, and how much more important they are. Furthermore, we often don't have a good idea where the minimum occur in our range of hyperparameters and how wide or narrow those minima or maxima are. For example, we see how grid search here can skip over an entire peak without even knowing it, and that it can be inefficient by searching over parameters that don't really matter too much. Both of these failures are ultimately due to us baking in our preconceived notions of what good hyperparameters and values to explore. Random search helps by selecting values randomly, and all we provide is the region of space to explore rather than the exact values to use. A considerably more difficult AutoML problem is trying to automatically generate neural network architectures for a particular task. The first step of making any neural network model is deciding its architecture. The process includes considerations like how many layers should I use, what type of components are those layers, for example GRUs versus LSTMs. You should use regularization schemes like dropout, and which layers that we should apply dropout on. In other words, our overall goal is to automatically generate neural network architectures that perform well on a given dataset or a given task. How would we even begin to tackle such a problem? Well, how do we ultimately figure out the best architectures as humans when we're designing it from scratch? We try out different combinations and we see what works. There is a particular area of artificial intelligence well suited for such cases, where we have some agent trying out various actions, receiving some reward for each action, and then using that feedback to figure out what to try next. It's called reinforcement learning. So here we're going to see a high-level diagram of a popular approach called neural architecture search, which uses reinforcement learning to learn which architectures are good and which architectures are not so good for a given task. Starting on the left, we sample a sequence of outputs from a recurrent neural network called the controller. At each time step, the softmax outputs of the controller provide a distribution over possible neural network components that we specify beforehand, and we select the component associated with the highest probability. The RNN or controller will repeat this until some predefined number of components have been sampled, and the resulting sequence of components defines the generated architecture. This architecture, called a child network, is then trained on the dataset of interest to convergence, and the validation accuracy, denoted R, is recorded. The validation accuracy is denoted by R because it represents the reward, R for reward, for the reinforcement learning model, whose goal is to maximize its expected reward, where the expectation is over the sequence of model components sampled to get the child network. In other words, the controller learns how to connect components together that results in the highest validation accuracy, expected. This is indeed quite similar, if you think about it, to ideas behind gradient descent, in that we are iteratively updating the controller RNN's parameter weights to maximize some function. Unfortunately, we don't have time to dive further into the details of neural architecture search, but I provided a link to the paper in the additional resources slide. At this point, it's probably becoming clear that the models we've covered today can require enormous amounts of computational resources in order to finish in any reasonable amount of time. For example, I've inserted a quote here from the paper introducing neural architecture search, which is from the diagram we saw in the last slide, and it casually states that they had 800 networks being trained on 800 GPUs concurrently at any time. No big deal, right? We all have 800 GPUs. They also go on to say that they end up training 12,800 architectures total. In other words, it's essentially impossible for most people like us to reproduce current research results in AutoML. Trying to find more efficient and less brute force approaches for AutoML is an active area of research, so hopefully this is no longer true by the time you're watching this. Fingers crossed. And as always, make sure to read through the links here for an in-depth look at the topics covered today. Coming up next, TensorFlow Eager. TensorFlow Eager is TensorFlow's new imperative, defined by run interface, where operations are executed immediately as they are called from Python, similar to NumPy.